So now if we have one current infinitely long while carrying current out of page this way, I, and at a distance r, we are going to have a B field like this. The B field is looping around the current. We use the right-hand rule to determine that. And we can go through the entire Ampere's law step by step and figure out that B field multiply this 2 pi r equals to mu 0 I. So B field created by this while is equal to this much in this particular direction. You cannot just memorize this, and you have to go through everything step by step. Now, what if I have, instead of one while A carrying current out of page, what if I have another while B carrying current into the page? Okay? So we can do the same thing. If we have a current into the page, use our right hand, align our thumb along the current direction, bend your forefingers around it, and then in this case, we are getting clockwise the B field. And at the location P, the B field loop is going to look like this, and it's clockwise. Okay, and it should finish the entire circle. And then now we do the same thing for this part. We're going to get the B multiply the 2 pi r, the same r, suppose this is the same distance r, equals to mu 0 I. And then I created a B field using this while. In which direction? A clockwise, counterclockwise, this way. The tangent direction of the B field due to A is this way. And the tangent direction due to B is also in the same direction in this case. And then this is BA, and I have a BB equals to, so that's in the negative J direction coming down. And then this is mu 0 I over 2 pi r in also the negative J direction. And then the total should be the sum of these two. Okay? And you may ask, wait a minute, how about what's going to be happen if I would like to draw a circle surrounding both of them? If I'm drawing a circle surrounding both of them, the total current into the page, out of page cancel out. Left no current, and this integration gives us 0, which means B field equal to 0. No, but be careful. When we do this integral, and when we eventually can take out B multiply a length, we need B to be parallel to ds or perpendicular to the ds, and we also need the B field to be constant along the loop. So it is true that if you choose a bigger loop surrounding outside, the integral of B dot ds would be 0 for that big loop, because the amount of current penetrating the big loop is positive and negative. The two I cancel out. But that does not mean you are having a B field equal to 0 everywhere. That's simply because in this region, you have the B field mainly upward due to this while, and you are not influenced by that while as much. However, in this region, when you have the B field created by this while, it's typically downward. So as a result, on this side, you have a strong B field upward, and on this side, you have a strong B field downward. When you integrate in the whole thing, you get something 0. It does not mean everywhere in between the B field is 0. Okay, that's important. Next, if we are talking about another problem, also, by the way, it is a coincidence that these two whiles at the center, exactly the two B fields are in the same direction. You can imagine having another wire here, and then the B field created by one of them and the B field created by another of them could form an angle. And when you add the two vectors at an angle, you need to be careful and decompose the XY components. And next, if we have something like a current carried by a wire, initially I have a very small wire with a small radius I. Now I carry the same amount of I with a much bigger, thicker wire. And what's going to be the B field at the center, at the surface of the wire? In this case, at the surface of the wire, I have a small 2 pi r multiply the B field equals to mu 0 I. Here, if you do the same thing, you're integrating the same thing, but at a bigger distance, bigger circumference. Again, you have the same amount of I, but you are having a small amount of B multiplying a longer circumference equal to the same amount of mu 0 I. So when the two wires are carrying the same amount of I, this one on the surface, the B field is less than that one. When the one wire, infinitely long carrying current going through, the resulted B field closer to the wire is stronger. And the resulted B field at a distance larger and larger is going to be smaller and smaller. What if you have a wire? So this is the entirely solid wire, okay? And then inside the wire, current is going through at every location. How about let's figure out the B field at a location B inside the wire. And then we can also do the same thing due to the symmetry. We know the B field would loop like a circle centered at the center. And then again, along this loop, we have the integration of B dot ds. And this is a small radius r. And again, that's equal to B field multiplied 2 pi r. And in this case, it is not equal to mu 0 multiplied the entire I. No, no, no. It is mu 0 multiplied I inside. Inside what? Inside our integration loop is this part of I. Obviously, this part, current flowing, is less than the total amount. And then by looking at the area of this shaded region, comparing to the total area, the ratio between them is going to tell you how much current is actually included in this part. Also, Ampere's law can be applied to some other situation when the B field is symmetric so that you can find a loop to do this integral easily. One is the example of a solenoid. Very, very densely packed rounded wires and a pretty long coil. And then in that case, the B field inside is pretty uniform. And the B field outside is 0. And then you can choose such a loop, a rectangular shape. And then this integral become B multiplied the length L for this part, plus 0 and 0 when the B field and the ds are perpendicular to each other. And outside the B field is 0 anyways. So in this case, we have in this integral B dot ds for this entire red loop is equal to B multiply L plus 0 plus 0 plus 0. And that's equal to the amount of mu 0 multiply the current penetrating this loop or enclosed in this loop. However, if I'm sending current I through these wires, the enclosed current is not 1 times of I. In this case, that's going to be counting 1, 2, 3, 4, 5, 6, number of n turns penetrating this loop. That times I. That's the total number of current penetrating this loop. And then you can easily solve for the B field inside this case, which B is equal to mu 0 n I over L, which is equal to mu 0 little n L, and the little n is the ratio between the total number of coil over L, which is the coil number density, length density, every meter or every centimeter, how many turns that you have. The same idea can be applied when you have a densely packed coil which are bended into a circle, and then the B field inside forms circles, and then along this circular path you will be able to apply Ampere's law, and you find out that the B multiplied the 2 pi r of this particular circle, you're going to be equal to mu 0 multiply the total number of n, many of current penetrating this circle, and that multiply I. Okay, and that's the examples for applying Ampere's law.